Hello. So, good day, everyone. My name is Diana Rose S. Gilbuena, and the topic we will tackle today would be about the center and commutator subgroup. For introduction of group theory. So, to start, let us first recall what is a group. In definition, a group is a group G is a set with an operation satisfying closure, associativity, identity, and invertibility or inverse. So for us to enable to know what is a group, it should satisfy these operations. And the key terms for this, we have the group operation, which is dot, the identity element, which symbolize E, and the inverse element is symbolized G inverse, which have the like the exponent in that -1 that is called or read as inverse. So commutator subgroup, every non-abelian group G has two important normal subgroup, the center Z of G of and the commutator subgroup C of G, which the Z symbolizes as the German word Zentrum, which means center. And the center Z of G is defined by Z of G is equals to the set containing Z element of G such that Z times G is equals to G times Z, for all G is an element of G. So in exercise 552 or section 5 shows that Z of G is an abelian subgroup of G since for each G as an element of G and Z as an element of Z of G, we have G inverse and G inverse is equals to ZE is equals to E. We see at once that Z of G is normal subgroup of G. If G is abelian, then Z of G is equals to G. In this case, the center is not useful if it is a commutator. So we have here the example of commutator subgroup. The center of a group G always contain the identity element E. It may be that Z of G is equals to E, in which case we say that the center of G is trivial. For example, examination of table 8.8 for the group S sub 3 shows that Z of S sub 3 is equals to P sub 0. So the center of S sub 3 is trivial. This is special case for the exercise 38, which shows that the center of every non-abelian group of order PQ for primes P and Q is trivial. Consequently, the center of S sub 3 times Z sub 5 must be P sub 0 times Z sub 5, which is isomorphic to Z sub 5. Turning to the commutator subgroup, we recall that in forming a factor group of G modulo a normal subgroup N, we are essentially putting every element in G that is in N equal to E, which is the identity. For N forms our new identity in the factor group. This indicates another use for the factor group. Suppose, for example, that we are studying a structure of all group G. Since Theorem 11.12 gives a complete information about the structure of all sufficiently small abelian groups, it might be of interest to try to form an abelian group as much like G as possible. An abelianized version of G by starting with G and then requiring that AB is equals to BA for all A and B in our new group structure. To require AB is equals to BA, is to say that ABA inverse and B inverse is equals to E, which is the identity in our new group. An element ABA inverse and B inverse in a group is a commutator of the group. Thus, we wish to attempt to form an abelianized version of G by replacing every commutator of G by E. By the first observation of this paragraph, we should then attempt to form the factor group of G, modulo the smallest subgroup we can find that contains all commutators of group. So, commutator subgroup has a theorem 15.20, which is let G be a group, the set of all commutators A, B, A inverse, and B inverse for A, B is an element of G, which is the generator of a subgroup C. C is the commutator subgroup of G. This subgroup C is normal subgroup of G. Furthermore, if N is a normal subgroup of G, then G divides N is an abelian if and only if C is less than or equal to N. So to prove this theorem, the commutator certainly generates a subgroup of G. We must show that it is normal in G. Note that the inverse ABA inverse, B inverse, inverse is a commutator is again a commutator, namely B inverse, A inverse. Also, E is equals to E inverse, E inverse is a commutator. And theorem 7.6 then shows that C consists precisely of all finite products of commutators. For X is an element of C, which is C is a commutator, we must show that G inverse XG is an element of C for all G is an element of G. Or that if X is a product of commutator, so if G inverse XG inverse for all G is an element of G. By inserting E is equal to G inverse. Between each product of commutators occurring in X, we see that it is sufficient to show for each commutator CD, C inverse, and D inverse that G inverse times CD, C inverse, D inverse, G is in C. But G, to prove this, we have G inverse times CD, C inverse, D inverse times G is equal to G inverse, CD, C inverse is multiplied to E and multiplied to D inverse G, which is equal to G inverse, CD, C inverse is equal to GD inverse, DG inverse times D inverse G, which implies to G inverse C multiplied to D and D multiplied to G inverse C inverse D inverse DG inverse D inverse G, which is in C, the C is normal in G. The rest of the theorem is obvious if we have occurred the proper feeling for factor groups. One doesn't visualize in this way, but writing out that G divides C is abelian follows from AC BC is equals to ABC is equals to AB multiplied to B inverse A inverse BA multiplied to C, which C has been like factored out, is equal to AB B inverse A inverse multiplied to BA times C, which is equal to BAC is equals to BC times C. Furthermore, if N is a normal subgroup of G and G is an abelian, B inverse N times A inverse N, that is AB A inverse B inverse N is equals to N. So AB A inverse B inverse is an element of C which is less than or equal to N. Then AN times BN is equals to ABN, and it will equal to AB, which is AB multiplied to B inverse E inverse BA multiplied to n, and this result to ABB inverse, A inverse multiplied to BAN, which is equal to BAN and equal to BN times N. So, for example, for the group S sub 3 in table 8.8, we have the table here. We find that one commutator and is P sub 1 mu sub 1, P sub 1 inverse, and mu sub 1 inverse is equal to P sub 1, M sub 1, P2, P sub 2, M sub 1 is equals to M sub 3, and M sub 2 is equals to P sub 2. We similarly find that P sub 2, M sub 1, mu sub 1, P sub 2 inverse, and mu sub 1 inverse is equals to P sub 2, mu sub 1, P sub 1, mu sub 1 is equals to mu sub 2, mu sub 3 is equal to P sub 1. Thus, the commutator subgroup C of S sub 3 contains A sub 3. Since A sub 3 is a normal subgroup of S sub 3 and S sub 3 divides S sub 3 divides A sub 3 is an abelian, and theorem 15.2 shows that C is equals to A sub 3. So we will base here in the table 8.8 to prove the example. So for the center of a group Z of G, the center of a group written Z of G is the subset of element in G, which commute with all elements of G. If G is a billion, then Z of G is equals to G. If G is non-abelian, then Z of G may consist only of the identity, or it may have other elements as well. For example, Z of D sub 4 is equals to R sub 0 and R sub 180. The center of a group is the subgroup of that group. And this shows that every center or a center of a group is a subgroup. So that's all for my report, and thank you for watching.